Okay, so in this video, we want to look at the concept of the span of vectors. As you'll see, it's actually a very straightforward concept, and again, this will allow us to simplify the way we think of these infinite objects such as lines, planes, and as we will see later on, other spaces of infinite spaces containing an infinite number of elements. So suppose we take again m vectors in Rn, and again Rn is a set of column matrices of length n. So we take m vectors. Here's how we define and denote the span of these m vectors. We write SPAN, the span of these m vectors. So v1, v2, up to vn. And all the span of vectors span is a synonym of generate. So the question is, what can we generate with these m vectors? And with these m vectors, we generate other vectors through linear combinations. And so the span of these m vectors will be the set of all linear combinations of these m vectors. So some multiple of v1 plus some multiple of v2 up to some multiple of vm. And again, we take all possible linear combinations of the m vectors v1 through vm. These are fixed vectors, and c1, c2 up to cm are allowed to range over all real numbers. So we simply write ci for any I can be any real number of our choice. So the span of these m vectors is the set of all possible linear combinations of these m vectors. So it's the set of all vectors that can be generated with these fixed m vectors. And that's it. That's what the span is. Let's consider now three simple but key examples of the span, and then we'll ask a fundamental question. But first, let's look at our three examples. What if I take R2, the xy plane? And remember that we will not look at R2 as tuples of real numbers, but as column matrices of length 2. So R2 is the set of all column matrices. If you think of them as points, the first entry is the x component of your point, the second entry is a y component of your point, and x and y are allowed to range over all real numbers. Well, let's decompose this vector as a sum of two vectors, right? We can write this as the vector x, 0, plus the vector 0, y, where again, x and y are allowed to range over all real numbers. And let's factor from this vector an x and from this vector a y, and let's see what we get. We get x times the vector 1, 0, plus y times the vector 0, 1, where x and y are arbitrary real numbers. And look at what we've done here. We have expressed R2 as the set of vectors or points of the form some multiple of the vector 1, 0 plus some other possible multiple of the vector 0, 1, because x and y are allowed to range over all real numbers. So this is the set of all linear combinations of the vector 1, 0 and the vector 0, 1. This is by definition the span of these two vectors, 1, 0 and 0, 1. And so we have reduced our thinking about R2, the xy plane, and again this is an infinite number of points, or if you think of the points as vectors, an infinite set of vectors. We have reduced it to just two vectors, the span of 1, 0 and 0, 1. And now think of it this way. If you ask, what can we generate with the vectors 1, 0 and 0, 1, the answer is the entire xy plane. And think of it geometrically. The vector 0, 1, 0 allows you to generate the x-axis of the xy plane, and the vector 0, 1 allows you to generate the y-axis of the xy plane. And we'll see later on that these are very special vectors. We call this vector e1, and we will call this vector e2. I won't elaborate on this for now, but this will come back very soon. So here's one example. R2 is the span of the vectors 1, 0, and 0, 1. We call this vector e1, this vector e2. Let's consider now a subspace of the xy plane, a line passing through the origin. So let's visualize this graphically. So we have our xy plane, and we will not consider the entire xy plane, just a subset or a subspace of it. Let's take the line with equation y equals 3x. So this is our line, and now we write the equation y is equal to, say, 3x. And I would like to write this line as the span of, you can possibly guess, to generate one line, you only need one vector on this line. Well, a natural choice would be the vector x equals 1, therefore y equals 3. So if x is 1, y will be 3. And now you have the vector, say v, x equals 1, y equals 3. And you can easily see that if you take all possible multiples of this vector, you will trace the line, right? If you take 1 times v, you get this point. If you take 1/2 of v, you get this point. If you take 2v, you'll get this point. If you take negative v, you'll get this point. So you can see that, at least on an intuitive level, every possible multiple of this vector will give you every possible point on this line. Therefore, the span of v should be equal to the line. Let's now prove this, and the proof will be very easily completed. The line is a set of points lying on the line, right? So we look for points xy. Well, given any x, the second component of our point or vector must be 3 times x. And x is allowed to range over all possible real numbers. If you factor x from this vector as a scalar multiple, you'll have x times the vector 1, 3. But again, as x ranges over all possible real numbers, what you have here is the set of all possible linear combinations of the vector 1, 3. Every possible multiple of the vector 1, 3. And so this is by definition the span of the vector 1, 3. If you prefer, the span of v. And you see, once again, we took an object in space, a line, that consists of an infinite number of points, and we have boiled it down to a single vector, the vector 1, 3. Because we're saying, what can we generate with the vector 1, 3 through all possible linear combinations? And the answer is the entire line. Let's do one more example. Let's consider, say, a plane in R3 passing through the origin. Let me take a different page. This will be our third example, and then we'll consider a more general but extremely useful and fundamental theorem. So if we want a plane in R3 passing through the origin, we have to give an equation where 0, 0, 0, the origin, is a solution. Let's take the equation x minus 5y plus 9z is equal to 0. Well, let's find the points on this plane explicitly by solving the linear equation, right? The points x, y, z that will be on the plane pi will be the solutions of this equation. So if we solve this equation, I've picked an equation whereas the linear system is already fully reduced. So we can write the solution set right away. Y and z are free variables, so we can handle those first. Let's say that y equals s, z equals t. Again, s and t are allowed to range over all possible real values. And if you solve for x, you'll get x is equal to 5y minus 9z, therefore 5 times s minus 9t. And now we can look at the plane explicitly. We have parameterized every possible point on this plane. So the plane consists of the points given by x, y, z, but we know what they are. The x-coordinate must be 5 times s minus 9t. The y-coordinate must be s, and the z-coordinate must be t. And again, s and t are allowed to range over all possible real numbers. Well, let's break up this vector as a sum of two vectors, the ones with s's and the ones with the t's. So vector 5s, s0, plus vector negative 9t, 0t. And finally, let us factor from this vector s and this vector t. So we will get the vector, well, s times the vector 5, 1, 0, plus t times the vector negative 9, 0, 1, where again s and t are allowed to range over all possible real numbers. And now think of what we have here. We have expressed the plane pi as the set of points or vectors of this form, where s and t are allowed to range over all real numbers. And if you break this up as into this form, you get any possible multiple of this vector plus any other possible multiple of this vector. But because s and t are allowed to range over all real values, what you have is a set of all linear combinations of these two vectors. You can call this one v1 and this one v2. And so the plane pi is simply the span of these two vectors, 5, 1, 0, negative 9, 0, 1. So there you have it. We have reduced the plane, which is an infinite flat surface, therefore contains an infinite number of points, or vectors, same thing, to two vectors. The span of these two vectors is the entire plane. So these two vectors alone are enough to generate every other point on the plane. So instead of thinking of the plane as this infinite set of points, we think of the plane now as the object that we can generate from these two vectors. Now, let's consider a more general question. And this will be the last topic in this video. That is, if we consider the entire n-dimensional space Rn, how can we test whether or not m vectors will span the n-dimensional space? And we'll find a really elegant and really simple criteria that will tell us whether or not vectors will span the entire n-dimensional space Rn. So let m vectors, v1 through vm, be m vectors in Rn. So all column matrices of length n, therefore with n components. And the question is very simple. Will these m vectors generate Rn, the entire set of vectors with n components? And that's our question. And you will see in the few next videos, this is a really fundamental question. If we're given a set of m vectors in Rn, so column matrices of length n with n components, will we be able with these m vectors to generate, through all possible linear combinations of these vectors, the entire set of vectors with n components? What we want now is to find a really simple method of determining whether this will be true or false. Let's just start with rewriting the span explicitly and trying to write it in a slightly different form. So the span, again, of vectors is the set of all linear combinations of the given vectors. So we get C1 V1 plus C2 V2 up to Cm Vm, where C1 through Cm are allowed to range over all real numbers. So Ci is an arbitrary real number for any I. And we know how we can rewrite a linear combination of column vectors, of column matrices, right? We know this is the same as the matrix times the vector of coefficients. So C1, C2 up to Cm. And the matrix is built one column at a time, where the first column is vector V1, the second column is vector V2, up to the mth and final column is vector Vm. Let's call this matrix A. So the matrix built one column at a time, where the ith column is the ith vector from our list. So if you multiply a column matrix by a rectangular matrix, the result ends up being, and you have checked this on the problem sheet about linear combinations, if you have a rectangular matrix times a column vector, the result is the first coefficient times the first column plus the second coefficient times the second column plus all the way up to the mth coefficient times the mth column. And recall that C1, C2 through Cm are allowed to range over all real numbers. Now, how could we write this much more compactly? Well, think of what we have here. These m vectors are fixed. We start with these m vectors with n components in Rn. They are fixed. And we're looking at all possible linear combinations of these n vectors. So this matrix is fixed, but look at this vector now. C1 can range over all real numbers. Same for C2 up to Cm. So because Ci can be any real number for any given I, we get here all possible column vectors with m components. And what we do is we take the set of every possible vector in Rm times this fixed matrix A. And we have a very special simple notation for this. What are we doing? By letting C1 through Cm range over all real numbers, this vector will range over all possible real vectors in Rm, and we're multiplying all of these vectors by the matrix A. So we say, well, we take Rm, we take every possible vector with m components, so every vector in Rm, and we multiply each one by the fixed matrix A. And this is how we write it. So when you write a matrix times a set, right, because Rm is the set of all column matrices with m components, when you write a matrix times a set of objects, what you mean is the set where every object in the set is the matrix times every possible element of this set. And now we can rewrite this equality much more concisely, because the span of these m vectors is simply multiplying every vector in Rm by the matrix A. So our question now becomes, or at least looks a little simpler. So all we've done now is we have reworded the question. The span of these m vectors is simply saying take every vector in Rm and multiply every vector in Rm by the matrix A. And will you get through this every vector in Rn? And that's the question. Let's look at this now and see why this makes sense, and also why this is a very familiar concept. Our matrix, if you go back, our matrix A is a matrix with real numbers. And what's the size of A? Well, the vectors are vectors, if you remember, in Rn. Therefore, they have n components. So we have n components, therefore n rows. And we have m vectors, therefore m columns. So A is a n by m matrix. And now we can view, and this is again is just rewording this equality, A is an n by m matrix. So think of it. You have an n by m matrix. If you multiply a vector in Rm, say vector u, well, Rm is a set of m by 1 matrices, right? M entries but 1 column. The product is defined, and the result will be a n by 1 matrix, but an n by 1 matrix is a vector in Rn. And so now we're just viewing the matrix where the columns are the vectors v as a function from Rm to Rn. And we're saying quite simply, if you take every possible vector in Rm, say x, and you multiply the vector by a, you get the vector in Rn. So send the vector x to ax. And as we have just proved, if you take a vector in Rm, multiply the vector by a, the result is a vector in Rn. And the question we're asking now, if you think of it, is the image of the m-dimensional space Rm under multiplication by a is the entire n-dimensional space Rn? And that's what we're asking. Let's consider now one simple result. And with that one result and elementary matrices, we'll find a really simple criteria when this is true or not. So here's a little theorem, and the proof will be really simple. So we'll let the matrix, say, C, be an invertible n by n matrix. Because C is n by n, if you multiply a vector in Rn by an n by n matrix, the result is also an n by n matrix. And here's a conclusion. Then, as long as C is invertible, if you take every possible vector in Rn and multiply those vectors by C, what happens to Rn? And the answer is, well, nothing. You get Rn back. So the image of Rn under multiplication by C is just Rn, as long as C is invertible. So we have to prove two things. First, that if we do multiply a vector in Rn by C, we have a vector in Rn. And second, that we can get every vector in Rn by multiplying the appropriate vector in Rn by C. Let's prove this, and the proof will be very straightforward. First, Well, we take the matrix C, which is an n by n matrix, and we multiply a vector in Rn, say vector u. But now vector u is an Rn, therefore is a n by 1 column matrix. So n equals n. The product is defined, and the result will be a n by 1 matrix. So this is a vector in Rn. So clearly, if we multiply a vector in Rn by the matrix C, the result is still a vector in Rn. So this proves that C times Rn is a subset of Rn. If you haven't seen this notation before, it means subset, which means that every element in here is an element in here as well. And you can see the elements in here are the vectors in Rn multiplied by C. But if you do multiply a vector in Rn by C, the result is also a vector in Rn, therefore lies in this set as well. Let's prove now that given any vector in Rn, we can find a vector in Rn where C times this vector will be the given vector in the range of our function. Well, this is the question. This is the second part of our proof. If we start with any vector in Rn, so the vector v, can we find a vector in Rn where C times this vector will be equal to v? Well, this is now where we use the fact that the matrix C is invertible. Think of it. If C is n by n, so is C inverse. So take the vector C inverse v. This is a n by n matrix times an n by 1 vector. The result is an n by 1 vector. And the action is multiplication by C. So of course, if you take the vector C inverse v and you multiply this vector by C, because multiplication is associative, we can perform this multiplication first, and we'll have C inverse times v. But of course, C inverse is I. We'll get IV, which is simply vector v. So if you want the image to be any given vector in Rn, say v, just pick the pre-image in Rn to be C inverse v. And C times this vector is vector v, which proves that we can attain any vector in the range by choosing the appropriate vector in our domain. So this proves that C times Rn is indeed Rn. So imagine what's happening to the space Rn. If you multiply every vector of the space by the matrix C, you get the entire space back, so it's just shifting the vectors around. That's all that's happening. No vector gets lost. We get back the entire same space. Just things have been moved around one way or another. And with this result now, we can go back and look at this problem, keeping in mind that as long as C is invertible and is an n by n matrix, we can multiply Rn, every vector of Rn by the matrix C, and nothing happens. We get Rn back. So our question was, we wanted to test to see if A times Rm was equal to Rn. And this is where we'll use now the previous result we have just stated and a familiar result about elementary matrices. So let R be the reduced row echelon form of the matrix A. Now we'll write R for reduced row echelon form of the matrix A. So imagine taking the matrix A, row reducing it to its reduced row echelon form, and calling the result R. we know we can use elementary matrices to prove that there exists an invertible matrix C so that C times A is equal to R. And if you think of it, A was an n by m matrix. Therefore, R is of the same size, n by m. So if you want to multiply on the left of A by this invertible matrix called C, C will have to be an n by n invertible matrix. So n equals n, and the result is another n by m matrix. And this was proved using elementary matrices, right? So given any matrix A and its reduced Roy echelon form, there always exists a matrix, which is, if you recall, the product of the elementary matrices, so that the matrix times A is the reduced Roy echelon form. And the key here is that C is invertible. And now we can use our previous result, which was, if you multiply Rn by an invertible matrix, nothing happens, you get Rn back. Well, let's do that now. We were asking, will A times every vector in Rm be every vector in Rn? Well, if and only if, let's multiply both sides by C, so C, and it's if and only if because we can go back to this equality because C is invertible. So we can cancel it and go back to the original equality. So CA Rm equals C of Rn. But this is our previous result. If you multiply every vector of Rn by an invertible n by n matrix, nothing happens. You get Rn back. And C times A, C was built from the elementary matrices used to row reduce the matrix A. And so C times A is the reduced row echelon form of the matrix A. So what we have right now is, you see the image of Rm under A is Rn if and only if the image of Rm under the reduced row echelon form of A is Rn. And now, I claim that we're basically done. Why? Let's just rewrite this equality as a linear system, right? We would have a rectangular n by m matrix times a vector in Rm, giving every possible vector in Rn. Let's write this in an expanded form and then look at the corresponding linear system. So we have the reduced row echelon form of the matrix A times a vector in Rm. So the coefficients are C1, C2, up to Cm. And we're asking, by doing this, can we get every vector in Rn? Say the vector is V and has entries V1, V2, up to Vn now. And now we can write this as a linear system in the form of its augmented matrix. We have a linear system where the variables are the coefficients C1, C2 through Cm. The constant terms are the entries of the vector V1, V2 through Vn. And the matrix is the reduced row echelon form of A. And now think of this. We're saying, given any vector in Rn, no matter how you choose V1, V2 through Vn, given any such vector, there always has to exist a vector in Rm so that R times this vector equals this one. So no matter how you choose these n real numbers, there must always exist a solution to the linear system. So this linear system must be consistent for every choice of v1 through vn. And this is a really, really important observation. So think about this. We have just said that the vectors v1 through vn will span Rn if A times Rm is Rn, but that's equivalent now to this linear system being consistent for any value of v1, v2 through vn. So now think of it. How can you have an inconsistent linear system? The only way is if you have a row of zeros and then a non-zero constant term. So imagine that we only have two options. Either the reduced row echelon form of A contains a row of zeros, or it doesn't. Well, if some row of R was a row of zeros, because we have total freedom on the entries here, if one row of R consists of all zeros, pick the constant term that corresponds to this row to be any non-zero value, and you will have an inconsistent system. But we have to have consistency for any value of Vn. Therefore, the reduced row echelon form of A cannot have a row of zeros. Well, what does that mean? If the reduced row echelon form of A cannot have a single row of zeros, it means that every row of R contains a leading 1. But now think of it. R was a n by m matrix. Therefore, there are n rows, and if every row contains a leading 1, the reduced row echelon form of AR must contain exactly n leading 1s. And that's it. We have the result we were after. The reduced row echelon form of AR contains exactly n leading 1s. And that's our conclusion. Let's write this as a nice little result, but you'll see that ultimately this is what we were after because it almost makes the problem a trivial matter. So what was our conclusion? And this is what we'll call a theorem. Let we have these m vectors, v1, v2 through vm, to be vectors with n components, therefore vectors in Rn. And the key matrix here was the matrix A, where the columns of A were built from these m vectors. So let these be m vectors, and the matrix A be built one column at a time using these m vectors. And recall that because these are vectors in Rn, they have length n, so this is an n by m matrix. So this is our setup, right? We said, given m vectors in Rn, build this matrix, and the question we were after is, will these m vectors generate Rn? And our conclusion is, if and only if the reduced row echelon form of this matrix contains n leading ones. And that is our conclusion. Then the span of the vectors v1 through vm will be all of Rn, so these m vectors will generate the entire n-dimensional space Rn if and only if the reduced row echelon form of A contains exactly n leading ones. And you see why this is so nice is we've taken a new concept, the concept of spanning of vectors, and asking, will these vectors, through all possible linear combinations of these m vectors, allow us to obtain every vector in Rn? This is a new concept, and we've reduced it to a very familiar concept. Build this matrix, we'll reduce it, and in the end, if you have n leading ones, the answer is yes, these vectors do span Rn. If your reduced row echelon form of A does not contain exactly n leading ones, the answer is no, the vectors do not span Rn. And that's it. I would like to add just one small remark, which is really, really important, and that is, why does this, or should this make sense on an intuitive level? As you will see in our next video, we will discuss the concept of basis and dimension. Now think of it here, and I'll use the word dimension, again very liberally here, but we'll define it properly in our next video. But think of it, our n consists of vectors with n components. And because every component, the first, the second, through the nth one, can be anything you like, you have n dimensions. And so if you want to generate, if you want to span Rn, you have to span n dimensions. And when you row reduce the matrix A, think of every leading one as allowing you to span to generate one additional dimension. So if these vectors will generate Rn, they have to generate n dimensions. And because every leading one allows you to generate one dimension, the reduced row echelon form of A must contain exactly n leading ones. Now, one last very short remark, and that is, sometimes you don't have to row reduce the matrix to know that the vectors do not span Rn. So there are sometimes shortcuts. And the shortcut here is very simple. Think of it. If you have an n by m matrix, when you row reduce, a row can never contain more than one leading one, and a column can never contain one leading one. So if you have to have exactly n leading ones, well, this means that given every column, you have to have at least n columns, because you cannot have more leading ones than you have columns. So if you have fewer than n vectors, the matrix A has fewer than n columns, therefore you will have strictly less than n leading ones, and the vectors will not span Rn. And that's a shortcut. If m is strictly less than n, the number of vectors is less than n, then you have fewer columns than n. So if you have m columns, you can have at most m leading ones, which will always be strictly less than the n that you need. So if you have fewer vectors than m, the vectors do not span Rn. and they will span something strictly smaller living inside of Rn. So always keep this in mind. And again, I will use the word dimension in a very liberal term, but the intuition is right. Rn is an n-dimensional space, and the word span means generate through linear combinations. So if you want to generate n dimensions, you need at least m vectors. So if you have less than n vectors, you cannot generate n dimensions. Therefore, the vectors will not span Rn. They will span something strictly smaller living inside of Rn. And what's nice, if you go back to the previous video and think of the concept of linear independence or dependence, the answer also lied in the reduced echelon form of the matrix, where the columns were the vectors of interest. So whenever you talk about linear dependence or independence of vectors, or the span being Rn, all you have to do is build the matrix where the columns of the matrix are the vectors of interest, and when you row reduce this matrix, you will simultaneously get the answer about linear dependence or independence, and whether or not the span of the vectors will give you all of Rn. So we have boiled down these two new concepts to the familiar concept of reducing a matrix and counting the leading ones.